there's really three factors that go into making a good flood forecast. The first is making sure you have the right ingredients for the different types of flooding that Dima touched on, as well as good model guidance and using probabilistic forecasting rather than a deterministic one model approach. And then, of course, verification. And all of that circles back to making a better forecast. If you're not doing verification, there's definitely some things that you can learn from your own forecasts and ingredients that you can get to know better to improve your forecasting. So for heavy rainfall ingredients, probably the largest and most important in Colorado is precipitable water. And that just has to do with the water vapor content in the column of the atmosphere, so how much moisture is available. We also look at the near surface dew points, so what's happening at the surface, as well as the moisture depth. So that has to do with the lower level of the boundary layer. And how deep is that surface moisture? Because sometimes if it's not too deep, it can easily mix out throughout the day. We also look at CAPE, which is the convective available potential energy, and the SEN, and those two work a little bit in tandem with each other. So the CAPE is essentially how much instability is in the atmosphere or the potential for bigger and stronger thunderstorms, whereas the SEN, or what we sometimes refer to as the CAP, has to do with not allowing the particle to necessarily reach into that CAPE and convective instability. So it's kind of acting as subsidence or sinking motion. We also look at your mid and upper level wind patterns. The upper level jet can sometimes provide extra lift when it's over the area, as well as steering flows controlled by that mid-level wind. And then there's the lower level winds as well, which is the low-level jet, which we'll talk about, which mostly affects the far eastern plains. But that can also contribute to heavy rainfall, stronger storms, and then by consequence, heavier rainfall. We also look at moisture convergence. So that's one of the reasons why topography is so important, especially over the elevated ridges of the Cheyenne Ridge, Raton Ridge, and Palmer Ridge. Those can create their own local circulations and moisture convergence, which can lead to heavy rainfall and storms. Then, as Dima alluded to, we have that unique mountain flow pattern where we get the differential heating between the mountains and the surface, and so we can get these upslope winds that initiate storms as well. And then one thing that we also look at is the warm layer depth. So that is essentially when you have a warm raindrop process. So that's when collision coalescence is what we call it in the meteorology world. And essentially you get drops running into other drops and it creates a really efficient rainfall rate. And that warm layer depth increases during the summer months versus the cold cloud process and rainfall development, which is not near as efficient. So this is the precipitable water climatology at Grand Junction, Denver, and Dodge City. A couple things I want to point out. On the bottom is January to December. So across all of these, oh, and in the bars are our forecast season. So that's May through September 30th. So all three show this ramp up of moisture during this warm season, which coincides directly to the heavy rainfall threat. Obviously, because of elevation differences, Grand Junction and Denver have less moisture than, let's say, a Dodge City, Kansas. But you can also see more day-to-day variability in the Grand Junction and Denver. And mostly if you just look at the black line, that's your average PW. And what's really unique in Grand Junction from about late June to early July, you see this huge ramp up in moisture, which is the North American monsoon. So there's really unique features, but again, why we focus on this May to September 30th forecast range is because you have this higher PW. So this is looking at rainfall over the Denver metro area. We have our forecasted PW on the x-axis, and then the max 1 hour rainfall that fell, or QPE, on the y-axis. And we've kind of created two separate lines that talk about the two humps of seasonality that Dima was talking about earlier. The blue line has to do with that early season spring dynamics, where the red line has to do with the monsoon moisture. And what you see here is PW and the potential rainfall doesn't really have a one-to-one ratio, but typically when you're above 0.5 PW, you have the potential for at least an inch of rainfall. And you have different dynamics at play during the spring season, which is that blue line. So you don't necessarily need as much PW to reach that inch an hour. So that's again on the, oh, and then on the right-hand side, we have the percent chance of exceeding 1 inch in an hour. So that corresponds to that threat table that Dima just went through with a low, moderate, and high. Just so kind of some reference of probability of exceeding that 1 inch of hour of rainfall given the early morning forecast across Denver Metro. I'm going to toss it back to Dima now to do a little bit of model guidance.
All right. Thanks, Dana. And yeah, so I think the thing to remember here with the model guidance and these ingredients that Dana discussed is that we're really, what we're embracing is a two kind of twin-headed approach where we focus on the conventional meteorology that we learn in school, but we're also trying to incorporate the latest weather modeling information and stay on top of what the research community is doing. And so to that end, what this table shows is just a huge list of all the different models that we consider on a day-to-day basis. And so I think there are a couple key takeaways here. Obviously, the details are not particularly important, but one thing to note is that the models all have different resolution. And so what we put a little more emphasis on is that the higher resolution guidance, because those are the ones that can more explicitly model the storm clouds and essentially are more realistic in their rain rate at forecasts. Now, having said that, Alyssa, if we step on to the next slide, having said that, even the highest resolution models are still essentially models. It's important to note that they're all in their model world. And so what we do every season is we typically establish these bias correction procedures where we take what the model said was going to happen and then we compare it to what actually happened, and we develop these curves that essentially allow us to translate what the model bias is. And the vast majority of the time, we see that the models are a little bit too dry across Colorado. And we don't know if this is just a Colorado phenomenon or if it extends outside of our state. But essentially, the vast majority of models are too dry, whereas a couple of models are a little bit too wet. So we do account for those biases to make a more reliable forecast in the end. So the next, what this shows is actually the forecast from the Boulder flooding event in 2013. It's from a researcher at Noah Ezra. And so all these different colors show possible rainfall accumulation across that event from a whole different range of models. And what you see is the black line is what actually happened. And I think the key takeaway here is that this ensemble approach to modeling, where you consider a whole bunch of different models as opposed to paying attention to any particular one, is by far the more superior approach, especially when it comes to heavy rainfall prediction. So let's see, if we step to the next slide, I think we discuss, yeah, okay. So this is, we just wanted to give a snapshot of kind of what we look at on a day-to-day basis. So we have what's called a QPF viewer that we've built. QPF stands for Quantitative Precipitation Forecast. So essentially your forecast of rain intensity. And so we have a bunch of different durations, a bunch of different thresholds. We have the maximum intensity, the chance of precip, the number of rainy hours. We have pretty much every metric you can think of. And I think one important takeaway here is that this is not, this looks nice. There's tons of information here, but it definitely doesn't replace the human eye in certain aspects. And I think what we're able to do with the product, though, when we use this kind of guidance, is that we're able to really hone in on the gradients. For example, what you see here is the forecast on June 1st, and you'll note that there's a big gradient in precipitation chances over northern Colorado, where it essentially goes from almost 100% to something like 20%. And so those are the kind of features that without guidance at this kind of resolution, we really can't pick up on that with the human eye. And so what we're trying to do is we're trying to assemble everything we've learned with our experience, but also put in that more kind of the honed in guidance to help discriminate areas that are higher threat. And so I think that's definitely an evolving thing of what we're doing. And this is another example of how model guidance is obnoxious on one sense, but also interesting in another. So what we have is the forecast for June 7th of 2022. And if we take the maximum hourly rain intensity across all of our models, something like 30 models probably, that's what's shown in the left map. Now, if we take a look at the right map, we see what any one particular model spit out that day. And the interesting takeaway is that what actually happened probably looks like more on the right side. It's what one model said. But the problem if we just follow the one model approach is that we lose track of all the different potential scenarios. So in this case, we lose track of that upper end intensity, the worst case scenario rain rates that are so crucial to forecasting flood potential. And so I think our approach is basically to consider the worst case scenario, but also the probability of that happening. And that's how we arrive at our threat levels. So reliability is kind of our primary concern, so to make sure that our forecasts are reliable. So that's the takeaway there. I think we wanted to do a brief recap of verification. So how do we verify our forecasts? And the interesting thing about verification is that there are 2 points to it. One is that it helps the transparency of our product. So if you look, if you go to our website, you can actually find season-ending reports that we put out in October and November that go through, and for every single day, we estimate the maximum rainfall intensity across eastern and western Colorado, and we essentially verify whether or not what we said was going to happen happened or didn't happen. So that's the number one driver for verification. And then number two driver is we want to improve our forecasts moving forward. And so that's, that's of huge importance, I think, to stay on the forefront of forecasting. And so to verify, obviously, we need some measure of rainfall intensity. And historically, we did this using rain gauges. But in 2014, we began to add gridded estimates of rainfall. Some of you have probably heard of this gridded radar estimated rainfall. And what we're showing here is basically the fact that if you just use rain gauges alone, this is for a project we did actually that we're still working on with the Mile High Flood District. What these little dots mean are they're basically reliable weather or rainfall gauges across the Denver metro area. And the little colors, the circular colored pieces around the individual dots represent an estimate of how far can that gauge sense. Essentially, if we say, okay, if we take a 2-mile radius around a particular gauge, what is the effective coverage of all the gauges? And so the incredible statistic that you get from this is essentially, even in the Denver metro area, which is probably one of the best gauged areas in the whole country, the chances of capturing your maximum rain intensity from one of these confined summer thunderstorms is something like 10% at worst to maybe 40 to 50% at best. And as you can imagine, as you step into other parts of the state where it's more rural and there are fewer gauges, the chances of you capturing that maximum rain intensity is very small. And so that is why we added the gridded precipitation. So if we step forward, this just kind of summarizes why we have to use both rainfall gauges as well as radar estimated radar rainfall. And so the pros to the gauges is the accuracy. We know what fell because it fell in the gauge. It can be verified fairly well. The cons are that there's big gaps in coverage, whereas with the gridded products, they're full coverage in both space and time. They cover the whole state. They have hourly resolution, which is incredible. But the problem is that they have big biases. And so this is something that we have to battle with every day. And so the biases change depending on what kind of storm it was. If it was a warm storm with a big warm layer depth, typically these products underestimate the actual rainfall. Whereas if you have a whole bunch of hail, that fell, these products will tend to overestimate. And so we typically, it takes a lot of time to correct for this stuff, but it's extremely important to